Okay, so the problem was to solve the boundary value problem finite difference method. Okay, I had shown you the function. If you have written it down, these all like this matrix is the tridiagonal matrix. You will get constructing the tridiagonal matrix A here, because you will get after the idea of the finite difference method is you are converting a bound linear algebraic equation Ax equal to B. Okay, substituting the finite difference formulas. After that, what you will get? You will have A as a tridiagonal matrix, and B job is to find the x vector. As you can see, I have written the matrix A here. It is like you can see A I comma I. You can visualize, eyeball it, that the main diagonal is -2. Okay, and one above it, that is I plus 1, is 1. One below it is again 1. So it's a tridiagonal matrix. So matrix A is now defined. I am printing A, how it looks. So if you want to see, it looks like this. You can check, uh, except the first and the last, which are the boundary conditions. All other of the elements of the diagonal are -2. One above the diagonal is 1. One below the diagonal is 1. Yes. So this is the A matrix. And this is your B matrix, which you already got. It is like minus G. G value is 9.8 and H square is there. All right. The end value is 50. You have A, you have B. Now you can find X. How we are able to find? We are feeding A and B into this linalg dot solve. And it will give you the output of this will be the X vector. I'm storing it in Y. It. Yes. So this is your output. How it is, how the altitude is varying with time. Finite difference method. The same problem which we solved using the shooting method, we solved using finite difference. I think I gave you another function. Yes. Anyway, talk among like those who have done and try to do it. Okay. So last class we saw about how to classify a partial differential equation in parabolic, elliptic, hyperbolic, depending on the term b square minus 4ac equals to 0. So, form where you know A, B, C, F, and all like A, B, C at least, then you can classify your PDE as elliptic, parabolic, and hyperbolic. Depending on if b square minus 4ac is less than 0, it is elliptic PDE. If b square minus 4ac is equal to 0, parabolic. And if it is greater than 0, it is hyperbolic. So what kind of PDE it is? I think you found out that it is a parabolic PDE. Okay. So first we will cover elliptic PDE. Then we'll move to parabolic PDE. And hyperbolic PDE will be one of your. As you can see, the elliptic equation is like this, like two famous elliptic. Del to u equals to 0. Equation del to u equals to f. So something not 0 is there. F. Okay, so that's how they are different. You can write, suppose u is a function del to u as the partial derivative of second order with respect to u, with respect to x, and partial derivative of u with respect to y. Sum them up, that's equal to 0. A Laplace equation comes like in many practical problems, if you solve anything related to electrostatics, electro problems, yeah, you can definitely Poisson equations you will see more often in fluid dynamics. Okay. Solution of these equation is basically a function. So the solution is a u, and these are basically a function of both x and y, and they are usually defined in a closed, which is shown in the above figure. So this is a closed region. Mind you, this is a closed region R, which is defined, and you at every point inside the region R, you have a solution U. Okay. On the curve C. So C is like a curve, the boundary curve. And inside that, it is called a region R. How we are trying to solve it? We will construct a square grid. We will, and at each point of the mesh, you can find your solution. We will see what kind of numerical methods we can formulate to find the different values of not aimed at finding exact solution or analytical solutions, rather solutions at discrete points. The data you will find. That's the aim. This course is not aimed at solving PDEs. So as you can see, we have constructed this grid and we are dividing this region into a network of square mesh. Now it is not looking like a square, but assume it's a square. All right. So how shall we proceed with this? Suppose we know this equation, del 2u by del x2 plus del 2u by del y2 equals to 0. So how shall we proceed with this equation? Any ideas? Ideas. Whatever I have taught. Finite difference. You partial derivative given here, the second order partial derivative with respect to the like write it in form of finite difference method. In that way, not approximating the partial derivative with the finite difference method. Okay. So how shall we write? Anyone can proceed with it? I axis and this is your axis. Yes. Now this is an equispaced. That means from one point you can go to another point. You can write that this point plus h equal to this point. Yes. So similarly, you can just start saying like some formulas or something, so that we can start doing some numerics. Just one liner. After that, you will see automatically that just by magic the formula will come. Like we are taking a partial derivative with respect to x. It's most likely that your ith points will be varying. So how it will look? Yes. Always constant here, but the ith coordinate is changing. How we are doing? At that point, we are taking the before left point, and on the right side, we are taking the right point. Similarly, you can write for j. Yes. Yes, using finite difference. Now our job is, can you find Uij from this equation, from the above equation? Just one line. Carry a pen and all. Just eyeball things. You have minus 2ij. Then in the next term, you have minus 2ij. So that gets added up. It is minus 4ij. And since it's a minus sign and all other quantities are in plus sign, you can move that thing to the zero side. So that becomes 4uij. And all other things are on your left. So you can divide it by 4. Always know that h is not equal to 0. So you can always eliminate it. It's 1 by something non-zero. So it is a non-zero quantity. You can always eliminate. So how it looks? 1 over 4 times 12. So how this looks? So this kind of formulations, like evaluating one quantity depending on if you do for remaining kind of points, and in the history it has been known as red-black structures. Okay, red-black grids. So, say this again. This is your Uij. Okay, Ui comma j. Quantity Uij. This point is being evaluated based on yeah. I plus 1 j, I j minus 1, and I j plus 1. You can see how. So this point, in order to find this point, you have to take the average of the quantities of these neighboring points. You have to evaluate this point, you are taking the average of the quantity at these 4 points. So you can see how it looks. Structure. Yes. So same thing is drawn here. You can see your mesh. Delta x is h, and delta j is suppose k. It's not mandatory that you take the same grid size for the same step size for the x and y coordinate. And I plus 1, that means in x direction you I plus 1 j, keeping the j coordinate constant. I minus 1 j means you're moving. I j plus 1 means you're moving to the towards up 1. I j minus 1 moving down. All right. So very nice structure. So since you found this point, one of the points is taken for your, like, just for showing, for illustration purpose. But the numerical method is such a way that if you vary both I and j, you are going to traverse each of these nodes. If you vary I and j here, vary I and j. If you vary I and j, you are going to cover each of the nodes of the grid. Am I right? You don't have to find the values at the boundary because the values at the boundary will always be given to you. Can't solve. Boundary should be given to you. Okay. So this is sometimes known as a standard like 5-point formula. Points are involved in. Yes. So sometimes like if you see this figure sidewise and tops, okay, but it can be also, you can also imagine in diagonals. You can also imagine diagonals. Maybe I can show this in this figure. Like suppose this point, according to your standard 5-point formula, it was depending on this point, this. Now diagonal formula is also there. Where you don't need to take those 4 points. Maybe you can take this. Can you see how? Previously, now you're taking something like the diagonal. Why we have 2 different formulas for the same, to calculate the same quantity. So sometimes, like you might not be knowing value of one quantity. Maybe if you are trying to solve using the 5-point formula, you already know because it's a boundary condition. This quantity you already know because it's a boundary condition. But it might be that you don't know this quantity or this quantity. Then how? That case, maybe considering this, you are taking 3 boundary points. So you are reducing the number of unknowns. So in a case, if you know all the values, standard 5-point formula, apply that formula. If you see by applying standard 5-point formula, if some quantity is unknown, then that method is not working. Then you can move to the diagonal formula. Interchangeably, you can use. So why we are using 2? Only to find an initial mesh. So initially, all of these nodes are unknown to you. Yes, all of these nodes are unknown to you. Either standard 5-point formula or diagonal formula, you will first find method which I am going to teach you now. We will continuously, iteratively apply it to the same grid size, same grid points till they get refined. So we'll see the values at these grid points as they evolve will be constant. They won't change. Then you can stop your scheme, running your scheme. Then you have achieved your solution. Okay. So you can see why this is important, why we have taken a square grid. Imagine like you have a very big steel plate and yeah, like it is getting heated somewhere. Then how the heat is getting distributed? Obviously, there you can't apply like a continuous function formula. You don't have a formula there. What you can do, you have a machine which can record temperature at each of these points digitally. Yes, then you know the temperature at each of these points. So, and some points you don't know. You can use this method to find the temperature at the unknown, how the temperature is spreading. Yes, that is a one of the examples. For the diagonal formula, can you think how the diagonal formula works? Think about this point uij and start applying the diagonal formula, how it looks. Obviously, you will take these points, right? Point. So how will I write? So this is known as the diagonal 5-point formula. So how can you write uij? Again, it will be the mean of all your diagonal points. What are those diagonal points? How you want to find the coordinate of this point? You are here. Go one step back, that is I minus 1. Go one step further, that is j plus 1. So now you know the coordinate of this guy. You I minus 1, comma j plus 1. Plus, you are here. You want to find the coordinate of this point. Go to the right, that means I plus 1. Go above again, that means I plus 1, comma j plus 1. Plus, you are here. You want to go here. How? Go down. You I minus 1. Go toward the left. J minus 1. Plus, what about this point? Go down again. I minus 1. Yes. Then, sorry, did I say something wrong? If you go down, minus 1 it is, right? Point, you are coming down. That means you are decreasing the j value, j minus 1, but you are going right. That means you are in I value. So you I plus 1, comma j minus 1. Diagonal 5-point formula. So you have the standard 5-point formula. This is the standard 5-point formula. And you have the diagonal 5-point. Although these are very less accurate methods, but they serve as a very good approximation for initial. Okay. So as I told you, like after you obtain these initial values of u through this method, either standard 5-point formula or diagonal 5-point formula, you can improve their accuracy by using two methods. To improve the accuracy, by iteratively applying one is known as the Jacobi's method. There is the Gauss-Seidel. Might have learned about Gauss-Seidel and Jacobi a bit in your previous semester, solving the roots of the equation. I'll just write it here. So it's the same. It's the same as your previous method. Nothing new as compared to the standard 5-point formula. You take the standard 5-point formula and just change the indices. I will write the Jacobi formula first. It's Jacobi's method. What we do is, suppose you have applied continuous method. Suppose you have applied continuously your method, that is uij again and again. After n steps, the value of uij, I am denoting it by this. Derivative value of uij is denoted by this quantity, right? Formula the mean of 1 by 4 of 5 minus 1 j plus ui plus 1 j by j plus 1, the top guy, and the bottom guy, ui j minus 1. But there is a catch. Since I am evaluating the value of uij at n plus 1 step, so it will depend on the nth step. That's how the iterative. So here all the quantities will be n. All will be evaluated at the nth step. Jacobi's method. Value of uij at the next step. Now you will see how Gauss Seidel is very similar, but again the same quantity on that time is equal to 1 over 4 5 minus 1 j plus 5 plus 1 j ui. Just depending on n. So I'll mark those first here n. Then there is something new here. The other two quantities, they will depend on the n plus 1th times. Yes, previous method where all of the quantities neighbor, they were dependent. Now in the Gauss Seidel method, two of them n plus 1th step. Yes. So yeah. So we'll try to see. Usually you can see Gauss Seidel method actually converges faster as compared to Gauss Seidel method will be slower, but it is faster as compared to the Jacobi method. Solve a problem by hand using both the Jacobi and the Gauss Seidel method. So you have to find U1. However, what is the diagonal formula say to us? It is 1 by 4. Can you say the diagonal 1000 plus 1000 again plus 2000 is there. Okay. We don't know the value of U4. So we are doing this diagonal step, right? So I have put 1000, 1000 and 2000 here, but I don't know the value of U4. Just as an initial guess, we can put it 0. Just as an initial guess. 1000. U2. Advantage of that. So better you can use guess. It doesn't have to be right. It has to be approximate. So say I apply. So here I have applied diagonal 5 point. Suppose for U2 I can apply the standard form. This like what you say right, only for initial guess, only to get initial guess. I'm repeating again. This you can't carry after this step, only for this step only. Okay, I'm saying that really for the initial guess. It doesn't have to be that for all the mesh values you have to use standard 5 point. All the mesh values you have to use diagonal. You can use combined way, standard wherever you want, diagonal wherever you want, only for initial guess. After this one, no. Either Gauss Seidel or Jacobi, again and again iteratively till you find a solution. Standard point. That is this 1 by 4 of this plus this plus this plus this. All right. So 1 by 4 of 1000 on the top. U1 is just calculated like I'm going this way. U1, 1000 already known, plus U4, we don't know. This one, 500. What's that value? Then what you will find? And U3. How will you find U3? Standard 5 point formula. So it is 1 by 4 of U1. What is U? Already calculated 1000 plus 1000, 500, U3, sorry, U4. U4 we don't know. So set to 0. What value now? Now you can find U4. How will you find U4? Simply you can use that standard formula now, standard 5 point. U4, because U3 you now know, U2 you. What is U2? The other two will be just zeros, right? What is this value? Still guess. Now here it starts. First one you have to use Jacobi. Second one you have to use the Gauss Seidel from this. That is, these are the zeroth state variables. Now one, U2 of 1, U of 1, based on the values of the previous state. That's what is Jacobi method, right? The n plus 1 step depends on all of the variables at the end. Drawn this mesh right in your notebooks. So if I go to the next page, I think you will have the mesh with you. So for the Jacobi formula, I will just write the what you say, the first iteration, so that you get a kick like to start. Check your mesh. Whatever I'm writing, you check your mesh if I'm doing it correctly. Don't believe me. I'll write U1 at n plus 1 step. Again, just a average. Of course, it will depend all on the NS state for the Jacobi method. So you at the right hand side, you will see NS step. No n plus 1 should come. That's the correctness. Check if this is right. eyeball. Just eyeball the grid and check whether it is matching with your formula. And u2 n plus 1 as starting point is the important guess because you are framing a general architecture here. Then you can put n equals to 1, n equals to like so on. So this point will be important. The first, you are framing the general equations. So this will be the important step. So just check with your grid if I am going correct. Eyeball. Just eyeball the equations and match it with your grid. Fine. How many of you think that this is fine? Raise. Okay. So now what you have to do? This is the most important step in if you are asked to solve using Gauss, Seidel, or Jacobi method. You have to first write in a general way like this. This is your standard like 5-point rule. And you have to use the Jacobi method, that is computing n plus 1th step based on only n step. Yes. Now you can start putting n equals to 0. Start to 0 so that you will start solving on u for 1 because you already know the initial guess. N equals to 0 and solve. Just want your answers of this first iteration only. Then you can keep on doing this. Maybe till I encourage you to do till maybe 7th iteration by hand. Just to get a hang of this method. It's just you have to solve it one time, then you are good to go. So what are we doing? See the Gauss-Seidel method. At one point, if you are finding the n plus 1 time step, right? Then on the left part, you take the n plus 1 step, okay? And on one step. That's how you should visualize the formula. Don't like not memorize, but visualize the formula so right on your own. It's solved at n plus 1 step, and at the top, it should be solved at n plus 1 step. The rest 2 points should be solved. Agree? How? U I minus 1 j is your leftmost point where you are at. Okay. Then U I j plus 1 is your top level where you are at. N plus 1 step, others are n step. How many not clear? makes sense by looking at the grid. Standard 5-point formula. So one will be 2000. 1000 plus U3N. Right hand side, there is no n plus 1th evaluation. It's just these boundary conditions should have been evaluated n plus 1, but those are boundary condition and are constant. Check if it is true. Is it okay? Let me know. Fine. Two thousand plus. Tell me the other things. Not right. Hmm? Then plus 500 plus hmm? Fine. Yes. Wait. U2 n plus 1, then U2 n plus 1. U plus 1, okay, then yes, correct. So this is your general equation for the Gauss Seidel. Now what you will do? You know the initial guess. Now you will put n equal to 0 and try to solve for U11, U21, U41. Solve it and let me know what's the value. I will explain it again. We need boundary conditions without. I did. Thank you. So first of all, we need boundary conditions. If boundary conditions is not given to you, you can say I can't solve the problem. But boundary condition is being given to you, so you can say yes, I can solve the problem. So as you can see, these are the boundary conditions: T top, T bottom, T left, T right. That's what you need. The cross structure. Yes, you need the left, you need the right, you need top, you need bottom. Just imagine you as yourself like this. Yes. So then I'm giving you the initial guess. T guess is 30. I agree that this is not a good programming practice, but you can use the standard 5-point or diagonal 5-point formula and find T guess. Yes. Now you know the initial values. Now you know the boundary conditions. So yes, you can. Same thing. Think about how you started solving the problem by hand. Then proceeded for n plus 1 step. Please minimize your volume of WhatsApp notification. So you can see the color map here. cm.jet. Okay. You can take any other thing you want, not the jet. I'm asking you to explore this option. But for this program, I have taken the jet symbol. Okay, the jet. Okay. But you have to create a grid, right? You have to create a grid to see the distribution of the points. That is, I'm creating np.empty len x len y. It will create a set of arrays. The size is ln x and ln y on x and y directions. Fine with you? Yes. Now the array is empty. Array, right? And for that you need initial conditions. assigned, yes, a guess value, t guess. So that's what I'm feeling. Here you will come to learn a bit of new Python comments. T.fill. But this is the way how you learn the new things. All right. So explore what is jet, explore what is mesh grid, explore what is np.empty, what fill command. These you will see, like maybe in some application you just need array just based on one number, then you can use the fill command. Yes. Can you understand this statement here? The boundary conditions. Yeah. So just to have an intuition that boundary condition means it is a square grid. So obviously it will be on the top of the boundary of the square, bottom of the square, left hand side of the square, right hand side of the square. To do that, so what is happening on one of the grid, you will be there and scan the entire row. Yes. For the columns, what you have to do, start at one point and scan the entire column. Yes. So therefore, these columns are coming here. Something comma column. Okay. A big code, but yeah, just keep patience for this. So maybe I will share this code with you. Okay. Try to understand. Maybe at this moment, like it is a bit overflowing. Okay. But anyway, like try to understand what these comments does. Yes. I told you, if something comma colon is there, then you are scanning the entire row. Yes. Colon comma something is there. You're scanning one of the column. This is one of the basic things. Okay. Then yes, then it's fine. Then for maximum number of iteration, you are just up Jacobi rule, right? This formula is familiar to you. 0.25 is just 1 by 4. Then ti plus 1j, I minus 1j, ti plus 1j is your right hand side, my right hand side. Ti minus 1j is my left hand side. Tij plus 1 is my top. Tij minus 1 is bottom. And I am taking 1 by 4. So it's the Jacobi method. And you are keeping on looping it. How it decide which one to solve, that's how it is done in the loop. X and Y direction, you need to use a two for loops. And for the number of iteration, another loop. You don't have to understand each step of the code, but you have to understand how the code is flowing. That's it. You have to understand the logic behind it. You don't have to do the same way I have done. Maybe you can do in a better way. So this is how I am filling Tij based on the other in known values. Yes. Then you can do the contour F. So the value of t at x and y point, you have to use it. X comma y comma t. So at x comma y comma point, like those tuple point, what is the value of t at that point? It will be color coded according to that color. Therefore, we are using a color map. You can it has random values. Now I will say for one value, you give me red color. For a higher value, you give me blue color. Okay, that's what color map does. As you can see, depending on the values of t is starting from 0 to 96, the color is being distributed. The color is distributed based on the temperature, value of the temperature here. Here it's a temperature, suppose. So you can see 0th point there, the temperature is 0, then it is blue color. If it is 100, it is red color. Concept. You have an numerical value and you are converting into a color thing that is categorical. Yes. So mapping you are seeing. If you just see numbers, it is very confusing to you. But if you see the colors, it is more visual. So can you say which part of the square grid is at the highest temperature? Part of the grid is at the highest temperature. Highest temperature is like the red color. So you can see the topmost is at the red color, and slowly it is that is not only at one row, it is slowly diffusing. Okay, if you run it for longer and longer times, you can see the red would have diffused till the end of the grid. Now the below part of the bottom part of the grid is blue. That is, it is at lowest temperature. Bottom part of the grid is at the lowest temperature because it is blue, and blue is 0. Yes. So the more number of iteration you do, more number of time steps and all, you can see this red part is being evolved. Slowly it is diffusing now, right now. Yes. So I'll share this code with you. Okay. So yeah. So this is like the heat is call it a 1D diffusion equation. Yes. And there are many different schemes. We will see how to solve this. Like researchers, I think those who have read PDEs in their bachelors, PD in bachelors. So you might have learned about the heat equation, how to solve the heat equation. Yes. And you must have got how to solve it analytically. And you know, it is a very tough formula. A lot of summation and a lot of sign terms are there and very complicated looking formula. We will not solve that in this course. We will assume that it is being given to you, but we will solve using numerical methods. Idea is like how the heat is actually diffusing for the firecracker. Okay. What do you call that firecracker? One in loud voice. Apiti. So, yes. So, so as you can see, the heat is diffusing both in time and in length. So there is a spatial direction and there is also a temporal direction, that is time direction. Yes. So your function should vary with both t and x. That idea, time and length. Yes. So the equation which I'm going to write here. Okay, so x is the length of your firecracker. Yes. 0 to L. We want to see how it is diffusing, the heat is diffused till the point you are holding the rod. Okay. And maybe you can appreciate it and check it using your ABC values that this is a parabolic PD. How about something like an elliptic PD? Now we are looking into a parabolic 1D heat equation. Domain problem, like a open domain problem. You don't have a closed surface now. Everything is happening in open dimension. Yes. So again, like next class, we will again apply the same finite difference. You can apply finite difference to this part. You can apply finite difference to this part. And solve, right? Boundary conditions will be given to you. So here we will see very nice methods. One will be, I'll spill the beans. One will be the explicit method. One will be like implicit method. And then a combination of those two methods. There is some part and explicit some part. Then your method is becoming more accurate. Yes. So therefore that motivates us to a new scheme, which is a mix of both implicit and Nicholson scheme. We will just see that equation also. Okay. Derive the equation for the explicit part. Okay. like how the errors is there, and see that Crank-Nicholson and the implicit scheme are unconditionally stable. Whatever you take, it will always be stable. The method is stable. But your explicit scheme is conditionally stable. To motivate this, I would ask you one question. In numerical methods till now, as much as you reduce the step size of your problem, the more accurate solution you will get. Yes. Yes. But we will prove, we will show that it is not the case here. We will show that if you take some value below a certain point for the step size, then your method will go haywire. It will show random values. Okay, that means the method is not working. Okay, so it shows you, it motivates you that every time you can't take a very less value and feel that you machine learning also you can appreciate. One of few of many projects who are in their final year now, they did something on machine learning and they came across the same situation. However, they reduced after some tolerance. They found that it is not anymore working. So we will see that in the next class. That's it for today. So your assignment for today's class is to for the Jacobi, you have to implement for Gauss and do the hand problems for the Gauss, Seidel and Jacobi, the 7 and 3 iteration problem. All right.